All right, we're good to go.
So again, welcome everyone to the third and final session we're having at Chats. I guess you might call it discussion, whatever it might call it. So as you may recall from last time, we started first talking about how do we frame our problem and our decision-making process so that it would actually be more objectified, because often we are irrational decision makers. In fact, it's interesting because if you've ever seen the movie Beautiful Mind, the premise is that we're all logical, rational decision makers, when in reality, there has been a more recent movement to what's called afferent decision making. Afferency is basically based upon perception and also feelings, emotions. And the proponents of afferent decision making have been more and more showing that most likely people are not rational when they're making their decisions. So we're going to have to deal with that when we make our decisions, because simply put, some decisions are just made and that's it. And good luck trying to change anything throughout it. And you'll see why some of these happen, and that deals more with applied psychology. But as I was mentioning, the PROACT model might be a good way for you to develop out your problem so that when you get your alternative, you get some type of objectification within your model. Now, for what we were talking about for my economic valuation. And as I mentioned, the reason why that might be beneficial to the work here is because in addition to any projects we do here, or even when you go out into your work life, these decision models often are driven by money. And let's face it, depending on what company it is, that may be the all-encompassing driving force. Although you can kind of evaluate other parts of it using different types of models. But for the most part, most people tend to look at the money aspect. And again, I can't say it's always that way. For example, when I was mentioning about the prisons last time, let's face it, a lot of people are saying, why should I want prisoners to get educated and get a college degree when my kid can't even get to a community college or something like that? I can't go towards saying that, but in terms of economics, it probably makes more sense to deal with the economic issues. And in fact, if we went even deeper, you'll see that part of the reason why we have the problem is that they did not learn the skill background when they were younger. And indeed, there is this thing called the prison pipeline. It's often noted that much of it starts early on with education. So if you were able to get them educated early on through high school and junior high, a lot less people would be in prison. Unfortunately, that's another issue entirely. So let's say that after we've done all the work, how do we make sure that our models are good? That's the topic for today. And the reason why I call it robust decision making is because that's exactly what it is. How can we ensure that any decisions that we've made are robust, that they should continue to apply or not? And so that's why I was mentioning about the space shuttle. Now, when we get into this one, we'll also notice that's in the traps. But I think that what I'll do is I will talk about traps first, then get into some of the uncertainty. So what I mean by traps is in the late 1960s, after NASA had figured out, had been able to go to the moon, and mind you, that whole deal involves politics as well. Certainly it was a very dramatic engineering accomplishment to place ourselves onto another celestial body. The thing about that is that beyond the politics and all this, they were starting to realize, hey, there needs to be an economic component if we are to continue. And it's interesting when you look at the entire history of NASA, there were other mission alternatives. For example, there had been one consideration of the Gemini project where they were going to use paragliders to land them rather than land in the ocean. There were others that possibly they were going to take that and they were going to be able to use the Gemini to go to the moon. In terms of the Apollo program, there were considerations that they were going to make space stations out of it. And Skylab did actually become a space station per se, now, although not like the ISS right now, but they were able to make that. But there were other plans of how they would possibly use that to maybe build colonies or maybe get people to Mars and things like that. But these were all plans that never quite made it. But they did know that if they were going to economically exploit space, that they were going to have to consider how to get people in space relatively cheaply. And so thus was born the idea of a shuttle system. Now you have to understand that it's interesting when you think about this, because NASA thought of this back in the 60s, and we're seeing the commercial exploitation now with things like SpaceX, and then obviously the commercial aspect with the Blue Origin, and also the Virgin Atlantic one. I forget the name right now. But the idea behind it was that now space was a commodity. And it is, I mean, they found asteroids out there with an amazing amount of precious metals on them. One reason they want to go back to the moon is because that might be a more economical launch platform for other manned and unmanned missions around the solar system. And this goes beyond just pure scientific research. For example, they've noted that, like I mentioned, the asteroids, if you can get some metals from there, it might be easier to get them using them on Earth. Other things are the fact that it's simply easier to build certain types of materials in orbit or microgravity. And so that's why you would want to have some type of location with either the gravity reduced or in microgravity situations. So when they built the idea of the space shuttle system, it's a very interesting aspect. The particular one I want to show you is this particular diagram. Now, this figure is 0.1. This was supposed to be an economic analysis, more or less, of, or I should say, rate of return that they were anticipating. Okay, so you'll notice now, the first thing I think you'll notice is the number of shuttle flights. And as I showed you, the listing of the number of shuttle flights was only about 100, it was only 135. So the idea behind the shuttle system was that NASA was going to have flights almost every other week. And there are tons of stuff that NASA had planned to do with the space shuttle, some of which actually did work. The Hubble Space Telescope obviously worked, getting up the International Space Station, many satellites that were launched towards Jupiter and other planetary bodies. These all did eventually ride on the space shuttle, but they never became quite as robust in terms of the rate of return that they anticipated. Now, I'm going to mention that a lot of these factors were based upon the design and about an under anticipation of the technological complexity. One of which, and this is one of the big things that people have been arguing about, is that in the original designs, when we talk about this expendable rockets, one of the things that was noted is that these rockets, the command part, the part with the human, was always on top. So there was never any danger of falling debris. However, in the space shuttle, space transport system, the shuttle was on the side, and therefore that was probably what you might call the proximal cause of two shuttles being destroyed. I would say certainly the second one, which was the Columbia, when a chunk of ice, actually foam if I remember correctly, came off during the launch and slammed into one of the leading edges on the port side. And unfortunately, that left a gash about 3 feet. I think it was about 3 feet wide, not particularly big, but big enough that because of the way the shuttle comes in, the leading edge would have a lot of heat going in. And so basically the heat that was coming in spilled in kind of like a waterfall, and all the aluminum was basically exposed and superheated and basically vaporized, unfortunately, and that led to a catastrophic error. But again, notice that when they did this, the rate of return they anticipated was much higher, including the fact, if you notice the timeline, 1978 through 1990, Well, number one, we never even got close to 600 shuttles to start with. We never even got close to 500. Number two, we didn't have the first shuttle launching, I believe, until 1981. And although it did go until 2013, I think it was, I forget the last date. I'm checking it right now. 2011. It never quite made it, and even though they anticipated these rates of return. So that being so, that's why we have to consider the idea of what's involved when we make these decisions. Because unfortunately, it was basically all or nothing, and the Soviets continued on with their pretty much stable technology. And for a time, the Soviets were the only game in town, and we were trying to figure out how to fix the space shuttle. Well, one of these first problems that we have is what's called the sunk cost fallacy. And the sunk cost fallacy basically says that once you spend money on something, you tend to keep thinking of the cost that was spent as a now factor than what it was at that time. For example, a very traditional one is when we talk about, let's say, tickets to go to a game or a concert or some event. The thing about the sunk cost fallacy is that once you spend money on those events, or once you put that money down for the ticket, that money's gone. It does not matter if you go or not, the money is gone. Unfortunately, what a lot of people tend to do is they tend to look at it in terms of, well, I'm going to lose the money. Actually, you already lost the money. And so, like, for example, the one I talk about in my classes is, imagine that you had these tickets, and let's say that you spent $200 for 2 tickets for this event, and your boss tells you that they want you to work. Suddenly they say, we need to get this thing done, and so your boss says, you know what, I know it's kind of late, but I'll tell you what, if you do this, I will pay you overtime, and I'll make sure you get $400. Now, on the records, $400 is more than $200. So you basically, if you look at it in terms of what you made $400. You could argue that it's $200 actually, but the reason why you have to worry about it, the fallacy is that you've already lost the $200. Now, if you want to look at it in terms of overall worth, yes, you could, but then you'd have to put things like, as you saw yesterday, we had to discount when we used interest rates and the like. And maybe you might say, well, if I go to this concert or event, I have some enjoyment. So what's the cost of my enjoyment of this event versus the $400 that I'll make if I stay? So there's a lot of other issues, but the main part of that is the issue of the sunk cost. And what it does is it tends to lead to additional costs later on. For example, when the NASA, the space shuttle developed, because they had invested so much, that may have led to the first failure in the Challenger accident. Because have any of you guys had to take engineering ethics yet?
Yes.
Okay. Do they talk about the Challenger accident?
Yes.
Okay. So this will be very familiar with you. Yeah, Clyde, out of the things that you remember of that incident, what sticks out in your mind the most?
They really emphasized on the fact that all of the engineers signed the launch and they didn't consider the safety. So it was more towards the safety aspect, but they did talk about the economic aspect as well.
Okay. Well, the reason why I asked you in that, and you're right, I think, did they mention the famous line, take off your engineer hat, put on your management hat?
Yes. Now that you mentioned, yeah, I remember that one.
Okay. That's a very famous line that's mentioned when dealing with this. And the reason I mention this is because although the Challenger incident is a very great example in not considering engineering safety, there was a cultural aspect that was based a lot in the sunk cost fallacy. So here you are NASA. For the past 15, 20 years, you've been telling the US government, you know what, if you invest in us, we will make sure that we'll get up launches up. We'll make space travel very cheap for you. You've been telling the military that too. And suddenly you're starting to say we're operational, and suddenly you've had to scrub several launches, and you have also a very high profile launch because you have a civilian going up, like Christine McCullough, and you are having to say, okay, do we launch or not? So when the NASA, you see, originally what NASA would do is, because it was mostly experimental, they were very much of the mind that you have to make sure all of your risk analyses are done correctly. And only until they are done correctly and acceptable will we allow for launch. Well, when they were making their launch assessment, they were looking at the system of the solid rocket boosters, the SRBs. And when they assessed it, remember, we're talking about a system that was supposed to go up every 2 weeks, and they're not even making it every 2 months. That suddenly they're told, we got to get a flight up. So what happened is, because they had spent all this time, resources, and money in developing out the space shuttle and saying, we will get it up, and now all of a sudden it's a very high profile launch, the push was, because of the sunk cost fallacy, to get the shuttle going. And so it kind of overrode the technical concerns, which was they were known. Even Morton Thiokol, when they were first testing it, knew that there was a problem with degradation of the O-rings and the blowback system in the SRBs when it was getting cold, because they couldn't react quickly enough to the gases expanding and going out in the SRB. And in fact, I remember I talked to one gentleman who actually had been taught by one of the engineers on this project, and he said that when the Morton Thiokol guys really looked at it, they had estimated the risk to be much higher than was acknowledged. I mean, they were, and I think that in the end terms, they found and they expected that they should have about one failure in every 110 launches. And in fact, the system actually did perform up to expectation in the end. So we have 2 losses in almost 150 launches. So what I'm saying is that when you start making your decisions, one thing you've got to think about is what's already in place. How is that going to impact the rest of the organization? And if I'm making the decision, how that's going to impact it. So, like, for example, if we already have an EWB project, we might say, well, we haven't finished it yet. Well, you might ask, is it worthwhile to continue to sink additional resources into that project or not? Maybe it's best to just stop. But the sunk cost fallacy will often push for more resources being done simply because already enough resources have been placed in it. That goes also to the second aspect, loss. See, that's why I wish I could find the video. I'll find it later and post it. But basically, the video goes like this. You have a gentleman, and he has a coin, and he asks people, if you give me $1, I promise to give you $1 back if by tossing this coin, I get heads, and if it goes tails, you lose. And so a lot of people say no. He says, well, I'll tell you what. If I toss this coin and instead I give you $2, but if you lose, you give $1. Interesting enough, a lot of people still wouldn't take that bet. And I'll even ask you guys, if you were given a bet where the person said, I will give you $2. I mean, you give me $1 to play the game, but if I win, I give you $2. But if you lose, I keep the $1. How many would you take that bet? I'm just curious.
I'd probably take it.
Okay, Nicholas, Justine.
I'm not a gambler.
Okay, so you wouldn't do it?
No.
Okay, Jasandra.
Maybe.
Okay, Clyde.
Probably.
So it seems like most of you are a bit more risk averse. I mean, not oddly, but the reality is when going through that video, the vast majority had to go at least to $50 before they would actually take the bet. And those are what are called risk averse individuals. So what you often see out in the workforce, now it depends on the company, because some, like let's say others that are like entrepreneurs, they tend to be more risk taking rather than risk averse. So they'll probably take bets more often. But the point is that when you have the issue of loss, people tend to overvalue it. So for example, and to go back to the numbers we had, if you were to say to someone, okay, I did all the analyses and I found out that by doing this change, we will save $100,000. Don't be surprised if they say, yeah, but the machine that's currently in place is going to cost, the machine that you're asking us to buy is going to cost $200,000 to buy. And that, that's a risk. So yeah, but doing the math and checking the uncertainties, it looks like we'll make $100,000 even though we're going to spend $200,000. So it goes on and on, but the big point is that you'll often notice that people will be less risk averse and therefore tend not to care about how much money you have unless an extremely large amount happens. Although there are cases like the lottery in which that may not be so bad. For example, the lottery, it's interesting because, I remember doing the numbers for something else, and the chance of winning the lottery, actually, if you look at the utility and how much money you make versus how much you would do if you invest, I think, for 3 years, it's less than $1. So the point is that when you deal with loss and uncertainty, don't be surprised that when you give numbers, people are not going to listen to you because they think the value they're getting back is not high enough. But this also goes to something called uncertainty. And again, I don't want to go too much, but I'm more interested in these last two right here. This part, often we have different statistical methods of figuring out how much money we've invested. Okay. Actually, first of all, how are you on the traps? Are you okay with that?
Yeah, so far so good.
Okay. I just want to make sure I forgot to ask that. Okay. I guess the rest of you okay. Anyway, so to deal with uncertainty, we have certain aspects. And the first one is we can actually use things like statistical estimates to figure out how much these values will be in money. Beta distribution, joint probability, expected value, these are all mathematical methods. If you've taken statistics classes, you probably have not seen the beta or expected value. You may have seen joint probability, but the point of these is that you can use statistics to find what past performance like, and based upon those statistics, figure out whether or not it'll continue to be the way it has been. So for example, shooting dice. So oddly enough, the interesting about dice and craps is that the reason why they make the game the way they do is because it's actually based on probability. In that game, if you get sevens, that's the best roll for certain rolls. But the point is, 7 is the most likely combination of the game, but can also cause you problems. I don't want to get too much into this because this could take an awful long time, but just know that, for example, if you were to look at 10 years of data and notice that, hey, we see that the performance of these has been to have this cost, you could just use those numbers, and that could be the basis for your predictions. The problem, though, comes with these here. Now, the first, verification, is basically, this is something I want you to hope that you guys will all remember. Basically, all of us build models, and that's what engineers do. We build models using different types of tools, mathematics, mathematics based in simulations, linear models, probabilistic models. I'm sure, like, Nicholas, I mean, you base your models on like stoichiometrics, I believe it's called. And all of us basically have our own methods of making these models that tell us what we predict if we put something into it. The problem first is, did we make the model correct to begin with? Now, again, going back to the space shuttle, when they originally imagined it, one of the big parts that they were trying to do with return was the fact that they had to make it so that it was able to withstand the heat. And the way in which they did it was using these heat shield tiles. They were capable of dissipating the heat very rapidly, and therefore it wasn't even a blade. It wasn't a blade. It was basically radiative. But the idea was that it would dissipate the heat well. The problem was they did not take into account other mechanical properties. The fact that you had vibration, the fact that you had, well, actually vibration was the main one. And what they found was after the first several launches that many tiles would come apart. They'd fall off the craft. And that was because at the very beginning of the launch, the vibrations would basically just dump these tiles off. And although that did, I mean, there was almost one case in which one shuttle almost got destroyed because there was the tiles over a certain area of the wing got loosened and fell off. The only reason why it did not fail was because directly under those tiles was basically a steel plate, and the steel plate was just strong enough to avoid having any disaster occur. But what I mean by this is that although that they had placed these tiles and they had done laboratory tests and seen the tiles did dissipate heat, the problem was in verifying the shuttle model, they had under anticipated what other factors would do to remove these tiles. And in fact, as I mentioned, unfortunately, spectacularly, we found out with the Columbia that you lose the tiles in the right place, you have a disaster. So whenever you're doing any type of modeling, whenever you're trying to do any type of economic modeling or any type of decision, you have to ask yourself, am I doing the model correctly? Okay, so that's one of the first things I would always ask students once they finish, is the model correct? Based upon what I did, okay? Now, once you do that model, the second thing you get is, does the model match the world? Now, I'm going to be careful. I'm going to put that match the system. The reason why I say match the system is because often what will happen is that you have to deal with the real world. You have to make sure that when you build it, the real world accepts it, or otherwise you're basically placing it into a good box. Because as engineers, what we often do is we develop out a mini model, and that model, that box, is the performance platform. So I'm going to assume most of you have seen Apollo 13, or am I incorrect?
Yes.
Yeah, I've seen it.
Yeah, I have.
Justine? Yeah? Jassandra? Okay, it seems like all of you have. If you remember, that's how they tried to do a scrubber by taking one of the pure filters from one of the craft and put into the lunar module. They had to figure out a way to make the part fit, and they had to do all this work on it. Now, mind you, they over dramatizes it because, as I understand, they actually had considered that before, and they actually dug up that solution that they developed. But the idea was that they found that, hey, the model did work because it was able to work in the real system. But often what I tell students is, how can you even have a clue whether or not the models work properly? For example, I talked about the whale. Now, if any of you looked it up, poor little whale basically went kablooey. Unfortunately, because whale blubber and whale parts are not of the same density and composition as rock, you had whale blubber and bits of whale all over a highway. And unfortunately, there were also people, so people were getting pelted with different types of viscera. that was an example where the validity of the model was not correct because they anticipated basically that they would just pulverize the entire animal rather than it being smashed apart and deposited all over the beach. I often tell my students that whenever they build models, regardless of the class I'm making, how do I know I can trust your work? Because you can do the math. I'm not saying you can't do the math. And you can verify that your model is perfectly correct. But in the end, I'll ask them, how do I know the purpose for which you're putting it in actually will work? How do you know that if you put it into effect, it'll be acceptable? And I'll give them an example of this. Two examples, actually. The first is Taco Bell. Many years ago, as I understand, Taco Bell tried to place a restaurant in Mexico City. Anyone want to guess how that worked?
Not good.
It closed up within 6 months. And they basically tried to introduce American food disguised as Mexican food, and unfortunately it failed spectacularly because they really hadn't thought about where they were placing it. Now, a model that actually seems to work is McDonald's. Because McDonald's, I mean, have any of you visited a McDonald's outside of the US?
Yeah,
Where at Nicholas?
in Brazil, the one in Brazil is so much nicer.
What were some of the things that they offered there?
They offer passion fruit juice. They offer better quality burgers. Their ice cream machines actually worked, which was pretty cool.
Okay, good. The reason I asked that, because I went to McDonald's in Japan one time, and they had offerings such as, they call it ebi burger, which is basically processed shrimp. So they had made a shrimp burger. They had a nori burger, which was basically, they had some that had shrimp ink in it. Other countries in Asia, they'll have things like, let's say, mangosteen or lychee shakes. I think avocado in some cases, or even things like durian. But the thing that's interesting about McDonald's is McDonald's does not just place their model exactly in each place. It considers the system, the area in which it's being placed. So, for example, they will make what they have in, let's say, in the Middle East, the vast majority, if not all of them, serve halal food. So it isn't just that they don't just put in, it's supposed to be halal. In India, good luck finding a Big Mac because they do not eat beef for the most part. So their model realizes, hey, in validity wise, although we serve a Big Mac, probably a Big Mac is not going to make it in India. So they have to use things like chicken and the like. As I mentioned Asia, in Japan and China, Singapore and other countries around the area, they have different types of offerings, including rice in some places. Now, I'm going to ask this, maybe some of you have heard of it, maybe you, Justine. Any of you guys heard of a place called Jollibee's?
Yeah, I've heard of it.
Yes.
Okay. So, I guess you might call it Jollibee's is the Filipino equivalent of McDonald's, I guess. And it's kind of a bad kind of comparison, because Jollibee's, I think, is better in many cases. And it has different offerings. But Jollibee's is starting to make a pretty decent inroads in the US. Now, I don't know how much it's gone into the certain populations, but I certainly know that a lot of Filipinos love Jollibee or other ones like Seafood City or Goldilocks closed up. They were taken over by someone else. But there are a couple of different ones that are out there that have been making a lot of inroads outside of the Philippines, so they understand their markets. But the point goes all to this factor. When you're building this, are you making sure your system will support what you have and that what you've built is acceptable based on the system? So going back to our problems, EWB, these are actually two of the most important parts, because if we find that, hey, yeah, we can definitely use, yeah, you're right about that, Justine. They're usually, yeah, they're all together usually. Anyway, going on. Validity. So what you would do is you make sure that, okay, you say, hey, you know what, we're gonna build a let's say water facility. So we're gonna build a pump for them, and we have to make it self-sustainable because they don't have any type of they don't have electrical infrastructure. So we're gonna have to use something else, like some type of self-sustainable energy source. So you say, well, you use solar. You find out that, hey, it rains 50 to 70% of the time. Probably not going to be a valid solution because the system itself does not support it. So you may have to use alternatives that will be valid. Maybe you can use a gravity feed because it'll come from a different source. Or maybe you could use wind power because maybe they do have a lot of wind. It's totally up to the system and where you're building it. And finally, it brings us to this idea of sensitivity. Now, what I mean by sensitivity is basically what can throw things out of kilter. So for example, one thing we found during all this pandemic is that our systems can be overridden if we do not have ability to transport it well, or we're not able to put people into the model. That's why they're worried about issues it's interesting, the toilet paper issue. But another one that I actually worked with a student was the issue of getting water prepared for people, because they had a big problem with trying to maintain a water stock. Sensitivity relates back to when I build my model, what are the parts of the model that can change it, that can change my outcome very rapidly? Is it fuel? Is it the cost of beef? Is it maybe it needs like the chips? Actually, it's interesting how they're talking about chips in the world, computer chips. There's been a shortage in some places because areas that have been hit have not been able to supply them. Sensitivity is basically what are the elements that will cause the most problem to my models if they're altered, particularly those that there's a small alteration that causes a big fluctuation. Questions so far? Let me stop for a minute. You guys good? Okay. So I always tell students that whenever you finish up, ask these three questions. Is it verified? Is it valid? And what can cause my model to suddenly change? If you ask those three basic questions, that goes across the board to any engineering solution, you'll usually be okay. And I'll give you an example of where sensitivity came in. Again, I keep going to the space shuttle. The thing that was really a model for the space shuttle was temperature. So particularly the rocket boosters, solid rocket boosters, they had not anticipated it would be a big issue because it's interesting to say, but the space shuttle was basically developed to be a space pickup. Just dump whatever is in the back and off you go. Unfortunately, it was never quite that way. And one of the things that was sadly that they didn't realize until too late for the Challenger was that temperature was a big variable, and the system was very sensitive to extremely low temperatures. We're talking even as low as 50, because they were finding in the model, and correct me if I'm wrong, Clyde, if you remember otherwise, what they found in the model was that, hey, as we were approaching below 50, we started seeing degradation in the O-rings. They started to have what's called blowback of the gases going into the seam there. And so that sensitivity problem was being very quickly realized. And I think there was almost a half dozen or more cases where the model that they were showing that the temperature was having a significant effect on the solid rocket boosters and could cause explosions. And unfortunately, they went beyond the realms of the sensitivity analysis. And when we're talking about close to, I think it was like 30 or 32 degrees Fahrenheit, the system failed. And that was what they were showing. So the idea is that whenever you build your models, make sure you consider that as well. What will make it go off kilter really quick? And I think I will stop here and take any questions from you guys. Anything about this one or anything we covered throughout the 3 days?
Well, throughout the 2 days, I was thinking for the acronym PROACT. I think identifying a target audience is important to creating a solution set. Where would that fit into the acronym?
Repeat that again, Nicholas.
I believe that identifying a target audience is pretty important to creating a solution set. Where would that fit into the PROACT acronym?
Probably in objectives, because
Okay.
that's where you would define what's called the actors.
Is that like another constraint? Is that why?
Yes, because what you would do is, let me give you an example. Like, remember how we talked about McDonald's and food?
Yeah.
Let's say that our objective is to provide food that is non beef. So you have to make sure you make a constraint that will prevent you from having beef in the audience. Let's say if you went to India. So usually you would put it into the objectives part, because that's kind of like a goal that you're trying to meet. So you're trying to make sure it's set out that way. Although there might be an argument, okay, I'd say objectives, but you could say why not consequences. And the reason you could say why not consequences is that if you put it there, then you could always introduce a bad variable, which is what type of things you're serving. If you include it in the objectives, then you can remove it once you get your alternatives. If you put it in consequence, you say, well, if I serve beef in an Indian McDonald's, I'll reduce the number of people there. But if I assume that people won't buy beef there, it would reduce that constraint already. Okay?
Okay. That makes sense.
And in fact, I would even say that when we look at some of these things where we have sensitivity and validity, I would tend to say that these would go into the sensitivity would probably go into the consequences, or actually it might be folded into the alternatives with the consequence, because you have to do that to make the final analysis. The validity would actually be done after, and would be done after you do the model and also the verification. So those would make sure that this is a good system. You'd want to iterate it if it didn't seem like it would be good. I'm not quite sure what you mean, Justine, but would that be part of validity?
Oh, I was just asking about Nick's example, but you pretty much answered it. So do you think you could write it into the PROACT model, like where like sensitivity and verification validity would go, like in the notes, so that we know?
Right, what I'll do is I will put it with this. I would say sensitivity, well, see, this is where it's kind of weird, Justine, that its sensitivity is actually in the consequences, could also be in the trade-offs, and I'll explain why it can be in all of these. The reason why it could be in alternatives is because when I'm actually doing the, when I'm actually looking at it, I could actually encode it into my decision model. So what I mean by that is, if I ask myself, okay, what are the alternatives? Well, I'm going to serve beef, chicken, and pork. And so in terms of sensitivity, I could say, well, how will that alternative affect the market? Um, I'm gonna have to think about that a little bit, because I mean, there's an argument that goes in a lot of places in this, but I would tend to say, well, let me think about sensitivity, but validity and verification would be outside the model because that would be iterative.
Right. I think I was just getting it confused because of like the questions we would ask. Uh, Going into those like validity, you said like, does this
Mhm.
model match the system? So when Nick mentioned, like where would the target audience go? Like I was taking
Right.
into account, like, oh, does this idea match the
Right.
target audience, the target area?
I think, you know what, Justine, I think I might put in objectives for one particular reason. If I can recognize that that might alter my system, then it trickles down basically to the other three there.
Right.
But what I would do is there might be an argument for another one on this. Now, mind you, I'm not trying to alter the Keening Hystra model, Rifa model, but I would think that what I might do is I would put at the last part the validity verification and sensitivity at the end. That way, what I would do is, normally what I do with my students is I tell them, okay, you built this model. So you know better than I, at this point at least, let's see, oops, that's wrong. You know better than I how your model works. Okay, so what are some of the key aspects that are developed here? So I say, well, when I looked at it, I recognize that the model seems to be okay because it matches everything that we found. However, the validity may not be acceptable because we're noticing that in some of the markets, it doesn't quite seem to work well. Okay, why doesn't it work well? Well, because we realize that we might need to, like for example, we might need a special type of material if there's saltwater corrosion possibilities, or there might be hard water that we need to worry about, so that might change the flavor of something, or it's going to be very difficult for us to get a certain ingredient. That's probably why I might pull it out. But I think that there could be an argument that the best place in the PROACT would be in the objectives.
So putting verification, validity, and sensitivity at the end is kind of like a way to catch where you may have missed something or went wrong in the model.
Yes, because often what you do is you iterate.
Right.
So let me give you an example. Let's say that, let's go back to since we've been using pumps as part of a possible EWB project, or even solar cells. So what you would say is, okay, if we're let's say use solar cells. Okay, so let's say we want to use solar cells and we say, okay, what are some of the issues that might affect our model if we go with solar cells? So that kind of goes into the consequences, but we could even start at the beginning if we want to preclude that. And so you say, well, some of the things that might affect are, what's the projected amount of sunlight in the area, usable sunlight? What's the amount of return voltage that we're getting? How reliable are these cells? Because different types of cells return different types of percentages of energy. How can we store this? So what can we depend on for storing it? These would probably be going into the sensitivity analysis, and you might even say, how available are they? And then once we start that, then maybe we should go back and say, okay, let's this is what we made. Now let's go through it once more to see what, if there's anything that maybe is something a little bit strange, because maybe they're on a razor's edge. Then you do the verification, validation, and then refigure your sensitivity. Okay.
Okay. Yeah, that makes sense.
And again, if you guys have any questions when you're looking at projects for the term, we can go through it together.
Would we get in to contact you with your email?
Yes. If you want, just contact me an email, and if we have to get online, no big problem. Okay. Other questions? I guess I'll take that as a no.
What's the best method? What's the best method you could think of to actually solving a problem? I could only think of one currently, which is trial and error, but others must exist, right? They're just sort of escaping my mind right now.
Well, it's kind of interesting, Nicholas, because I think actually one of the best ways of solving a problem is using the 5 whys to boil down to first principles.
The five,
Like, I don't know if you heard the example of why Elon Musk got into solar cells.
I didn't hear about it.
Elon Musk is a very big advocate of using what's called first principles. So in terms of the solar cells, he asked, why is it so expensive to get a solar cell system operating for people, for the general public? And so he started investigating, found out, okay, this is why solar cells are so expensive, and this is what their yield is, and this is what you have to put some type of storage device, and so this is why that storage is so expensive. And so basically he kept asking, why is it so expensive? And by breaking it down to the very first principles, he was able to get some relatively good ideas of how to expand on it. So he focused on building better battery cells. He's focused on building better, more efficient solar cells. And he's made a living out of it. And I think that, I'm an advocate of that, in which I ask myself, okay, what is the basic problem? And can we go into any lower than that? And once you get into the basic problem, then hopefully you could start finding solutions for that.
I see. So yeah, I can try and implement that one day, the 5 whys. That's a really good method. You can employ that same kind of logic with a lot of things. Like instead of a lot of things are like pretty dang expensive. Like I was looking at the price of the greenhouse, constructing greenhouses, and that's ridiculously expensive too. So maybe using the 5 whys like Elon Musk did with solar cells, find a way to manufacture that for cheaper.
But that's interesting enough, Justin. I find that there's a lot of wisdom in history. Like for example, the Persians had a form of ice boxes. They had these huge buildings that were able to keep ice at the bottom of these. Basically, it was a heat pump, a massive heat pump. And so they were able to keep ice there pretty much year round by employing fluid mechanics, basically. I showed you the Chaka system, and basically what they built is a series of little of water retention wells that basically recharged underground water tables. The Aztecs, they developed out the idea of the Chinampa system, and they were able to use hydroponics basically in order to feed a massive city. We find that many different solutions from ancient times actually solve problems because they didn't have the technology we do. And I think, unfortunately, one of the problems we have in modern society is that we tend to overthrow our technology when there might be more simple solutions, because like even the Roman aqueducts are still in use today in many cases. And all they did was just employ good architectural techniques and a sound understanding of how water flows down a system. And they were able to make a massive set of aqueducts that to this day are marvels. And so that's why I say if you boil it down to the essential problem and try and find a way to work with nature, often you'll find really good solutions that boggle the mind, because they work with the system. They're already working with the validity instilled into them rather than needing other external components to keep it done.
So basically, utilizing old methods and old technology can help us create a solution to modern day problems.
I think in a lot of cases, yes. In a lot of cases, I'm not saying every case, because I mean, obviously we didn't have people going to space back centuries ago or aeon ago. That requires its own set of technologies and the like. But when we're dealing with things in the worldly system, a lot of things might be useful. I mean, unfortunately, the way things are now, haywire, that's what I mean about sensitivity, because we're seeing that some things are just totally out of kilter because of changing conditions. But for the longest time, a lot of these systems worked really well because they worked with nature and the system itself rather than try to conquer it. Okay. I hope this was useful for you guys.
It was useful to me, at least. I hope it was useful for the others too who attended this session and stuck with it all the way through. Whether this session helps you create solution sets or helps you track profit values or exactly how much you're going to make through a purchase or a project, or even today when it helps you think objectively and create rational decisions, make rational decisions. In any case, I hope this seminar like aids you as you're working through projects, or some of you are even working as you're doing your work.
And
And
again, if any of you want to reach out to me, feel free to do so. And again, I did this because it seemed like it was of use for you guys. If it works for you, please tell me it does, and like that. And I'm trying to boil down a lot of classes into very simple concepts.
right, and condensing all the information from, is this 1 or 2 semesters worth of content?
I would say possibly 3.
3 semesters worth of content, boiling that down into 3 days.
Yeah, because
I'd imagine you can't get through everything, but you try to get like the bare bones and hope this.
Well, let me put it this way. The economics part would be definitely 1 semester at 40/30. Decision-making would definitely be 1 semester. I believe it's 4190, IME 4190 or something like that. That's decision-making. In terms of this last part, probably that would be partly incorporated into the decision theory, partly into engineering ethics, and partly into a class on applied psychology. So yeah, about 2.5, 3.
Well, I believe all this information was really helpful. I at least managed to learn a lot of new things with regard to determining the feasibility of projects and actually making good decisions. So I'd like to thank you for your time and just, taking the time to explain all this to us.
I'm glad I talked a little bit. Okay. Well, again, if you guys want to reach out, feel free, but you take care, and I guess we can stop for today.
Yeah, if no one has any more questions, I believe we'll stop the seminar over here.
Okay.
I'm gonna post this recording onto the Google Drive, and
That's fine.
I guess even for the people who didn't attend the seminar, I'll send that Google Drive link to other people so that they'll have it as a reference.
That's fine.
One day.
That's fine. That's fine.
All right. Thank you guys for your time. I hope you guys have a lovely day.
Take care all. Thank you. Have a good day.
Thank you, you too.